Minutes are up to 93, so that's good. So folks, welcome to our special webinar in the Mars 2020 mission with Dr. Farah Alibay. We really appreciate her spending some time with us to explain what she's doing. And my name is Dave Chisholm. I'm the meeting chair from the Ottawa Centre of the Royal Astronomical Society of Canada. I'm also vice president of that centre. And I'm going to change screens here. A couple of things before we get started. While we're in a Zoom webinar, we cannot be Zoom bombed, but there are other security issues that you should be aware of. First of all, do not click on any links, any URL links that may appear either in the chat box or in the Q&A box, just for your own safety. As presenters, we will not be putting any URL links in any of those boxes. If you wish to ask a question, please do not use the chat box, please use the Q&A box. We will be holding all questions until the end of the talk, and then we will work our way through the questions. And you're welcome to use chat, but we will not be monitoring that, okay? And I see somebody's already asked a question. Okay, we will answer that in a little bit, okay? So I'm going to turn it over to Karim. And just a second, let me just spotlight you. Replace spotlight, there you go.
Excellent, thanks Dave. Hi everyone, welcome from the RASC Montreal Centre as well. As you've seen in the poster and the advertising for today's event, this is a co-hosted event by 3 of our RASC groups, and you'll meet our RASC Next Gen chair shortly. One of the things we've been doing lately, both from the Montreal Centre as well as a lot of the other centres, is some sort of a land acknowledgement at the start of our sessions, acknowledging the fact that the lands as well as the night sky is something that's shared with our Indigenous peoples and our First Nations. And I try to keep it contextual, and so I have the formal land acknowledgement there that you can take a look at that is appropriate to both the Montreal and the Ottawa region, but we're virtual. And so when we talk about the night sky, one of the interesting things to note is the fact that the view of the night sky, the view of the planets even, has been through ancient astronomy, through all of our different cultures. And the Cree actually have a really interesting way of talking about Mars in the night sky, and specifically Mars retrograde motion, when it moves back in our night sky as it starts to move forward, as the orbits between the Earth and the Mars change their relative position. And they call it Muswa Asak. And that refers to the moose spirit, because when moose are moving through lands or herding and they get spooked by something, they move in a full circle before they keep moving onwards. And so when you look at the retrograde motion of Mars in the night sky, you see that sort of a behavior where it kind of loops in a circle as it moves forward. So one of the neat things as we now start talking about exploring other planets and actually setting foot on other planets with humans, hopefully in the near, not too distant future, is remembering that our appreciation and our dreams of the night sky have been something that we've shared all along between cultures across the world. So again, welcome from RASC Montreal Centre, and I'm going to turn it over to Emily.
Okay, Emily.
Hi, everybody. Welcome from your other co-host, the Next Gen Committee. So the Next Gen Committee, if you haven't already heard about it, is to address the needs of current and future RASC youth members. I am the chair of that committee and also the founder. It was founded this year, actually, in August. And our main goal is to represent the unique viewpoints, values, and experiences of the Society's youth members as they apply to their RASC membership. So we plan on doing lots of very interesting events, and even making scholarships and different opportunities for youth members across Canada. So we really hope that you stay with us and that we can keep bringing these types of incredible opportunities for all of you, and for, you know, all the youth members that may be sitting at home watching this right now. So without further ado, we'll pass it on to the other speakers. So thank you so much for tuning in.
Okay, thank you, Emily. So it's my great pleasure at this point to introduce Dr. Farah Alibay, who's been a system engineer at NASA's JPL For the past 6 years, she's a flight systems engineer on the Mars 2020 team, the rover mission scheduled to land on the Red Planet in February 2021. She is primarily working on the mobility system for the Perseverance Rover, as well as supporting preparations for surface operations. Prior to joining the Mars 2020 team, Dr. Alibay worked on the InSight Mars lander, as well as its companion mission, the Mars Cube 1, the Marco CubeSats. She started out in Montreal, and then she moved to the UK and obtained an undergraduate and master's degree from the University of Cambridge, followed by a move to the States to obtain a PhD from MIT, all in aerospace engineering. So it's a great pleasure for me to introduce Dr. Farah Alibay. And I'm just going to stop my slides, and there we go.
Thank you so much for
I'll let you start
me.
yours.
Let me go ahead and share my screen. So can you confirm that you can hear me okay and that you can see my my slides?
I can see your slides. Yep.
Great, thank you. I had to swap audio while you were introducing me, so it's always fun while on Zoom. Well, thank you so much for having me and for the introduction. As mentioned, my name is Farah Alibay, and I'm joining you, I guess, from sunny California. It is 26 degrees C outside here today, so I'm wearing a t-shirt and shorts still. It's sort of the land of eternal sunshine. But I do have to say that I miss Canada a lot, miss actually having seasons. But LA is not a bad place to be either. So before we start, I kind of want to talk to you, give you a little bit of a reminder of my journey. I know it was in the introduction. I was born in Quebec. I was actually born in Joliet, which is, well, I was born in Montreal. I grew up in Joliet, which is just outside of Montreal. And like every good Canadian, I figure skated for 10 years of my life. I think this is my first figure skating show. It must have been 3, 2, something like that. I then moved to England when I was a teenager. I was 13 when I moved to England. Mostly because of my dad's job. I ended up in Manchester, which is in the northwest of England. And you see here, this is sort of my graduation year, I guess. In England, a lot of schools are single sex, so I went to an all-girls school called Loretto Grammar School. From there, went on to the University of Cambridge to do an undergraduate and master's in aerospace. So in Cambridge, England, if you've never been there, looks a lot like Harry Potter. Indeed, in fact, you can see the gown I'm wearing and can't quite see the background there, but I went to Trinity College and University of Cambridge, and if you look it up, it pretty much is Harry Potter. We dined in halls and had masters and things like that. It's quite fancy, quite the experience. But after that, I sort of wanted to change. And one of the challenges that I had at Cambridge, and particularly in England at the time, is that there wasn't much of a space program. You know, I had a degree in aerospace engineering, but it was all very aerocentric. I was mostly working on jet engines. And I always had that dream, sort of that childhood dream of working in space. And that dream started from seeing Apollo 13 when I was a kid. I grew up with Star Wars and Star Trek. I mean, I grew up in the 90s, so space was a big thing. And I always kind of wanted to work in that field. And when I finished my master's, I realized that it was so close in reach, but I wasn't quite there yet. So I ended up actually turning down a full-time job at Rolls-Royce in England and taking the leap to go do a PhD at MIT across the ocean. So I think at the time I thought, well, you know, I'll go try this PhD thing. And if it works out, then it means I'll be following my dream. If it doesn't, I can always come crawling back and I'll still have a degree in Cambridge. I'll probably be okay. And kind of just took that risk and left everything behind. It worked out, thankfully. I got my PhD from MIT, most specifically in space systems engineering, actually exactly 7 years ago. I think I defended in November of 2013. So I've been, I guess, a doctor for 7 years, and I joined JPL in February of 2014. And what you can see here is the picture you see here is a picture of me working on the Marco CubeSats that co-launched with InSight. It was sort of my first and second year of JPL. I was still young and bright-eyed. I think I'm still young and bright-eyed now, at least bright-eyed. And this is a picture more recently of me now that I work on the Mars 2020 mission. Would you believe it? That picture was probably taken at 2 a.m. or something like that after my shift. because we are certainly working around the clock right now, getting ready for Perseverance to get to Mars. So let me give you a little bit of a history of Mars exploration. And specifically, so far, as of now, JPL is the only institution in the world that has softly landed something on Mars. And that started with the Viking missions back in the 70s. But in terms of rover history, we had the Sojourner Pathfinder mission, a couple decades ago now, was the first mission to have a rover. And it was actually a technology demonstration that happened then. That was followed in the 1990s by the Mars exploration rovers Spirit and Opportunity, which you've probably heard of if you like anything space. So those two missions were twin rovers that were landed different places on Mars. And they were really, they were really the first big rover that was like, it was a rover mission. They were doing the science. It wasn't just a tech demo. And actually there were missions that were meant to last 90 days because we didn't really understand Mars at the time, and they were solar powered. So we weren't sure how long they would survive. They ended up lasting something like 15 years. So maybe we over designed a little bit. And they made some great scientific discoveries, but not only that, but actually we learned a lot about what it means to operate on Mars, what it means to drive a rover on Mars, what it means to design a rover that's going to Mars. And all of that was wrapped into a body of knowledge that led to the Curiosity rover, which landed on Mars back in 2012. And Curiosity was a big step up, right? It's a car-sized rover. It landed on the Sky Crane. It travels much faster than Mars exploration rovers, and it also has a radioisotopic source of energy, so it's able to survive longer as well. So that mission has been on Mars for 8 years now, and now Perseverance has learned from all of those missions, all of the lessons learned, all of the things that we have learned about Mars, about engineering for Mars, and that has been wrapped into the Perseverance rover. So, when we land these things and when we do these missions, we really are standing on the shoulders of giants and standing on, learning from everything that's been done before, but also paving the way for the future. And specifically in terms of Perseverance, we are preparing as part of this mission for the eventual arrival of humans at Mars. And I'll talk a little bit about how we're preparing for that. So here's an image of Perseverance. In terms of size, she's a little bit more than 6 foot tall. You can think of it as sort of like a Mini Cooper, but jacked up on 6 wheels with about a 30 centimeter clearance below it. So it's quite the vehicle. And most impressive is its robotic arm. And at the end effector here, just the end effector weighs 50 kilograms. So it is a huge end effector that has a set of tools that can be chosen for the rover to use. Let's talk a little bit about what Mars 2020 is doing. So you'll hear me use Mars 2020 or Perseverance. Mars 2020 is the name of the project as a whole. Perseverance is the name of the rover itself. So I tend to use them interchangeably, but just so that you understand why we use those two words. So Perseverance is a geologist, and most importantly, it's going to look for, Martian geology, but also astrobiology. So one of the big goals that Perseverance has is that it will be looking for evidence of ancient microbial life. And so let me take a step back here. There's a belief that a few billion years ago, a couple billion years ago, that Mars probably looked a lot more like Earth than it does today. We know it used to have liquid water. We know it used to have an atmosphere. It used to have a global magnetic field. All of those things we believe on Earth are stepping stones for life. And so we are looking for microbial life that could have developed back then, so ancient life. And the reason why we're looking for that, and not more evolved life, is because we're using Earth as an analog again. And back about 2 billion years ago, that's about what we had on Earth. So we're looking for those same signatures on Mars. But one of the biggest goals that Perseverance has is going to wrap up its ability to look for geology and astrobiology and select interesting samples that it will cache. So we're going to take a number of samples on the surface of Mars, put them in tubes, seal them, and then leave them on the surface of Mars with the eventual goal of going to pick them up. So there would be another mission that would go land on the surface of Mars, pick up those samples and bring them back to Earth. And that's part of the Mars Sample Return campaign. So really, Perseverance and Mars 2020 is the first stepping stone in that campaign. So why do we want to bring samples back? We're already bringing a suite of instruments. I told you we have 50 kilograms of instruments on our end effector. Well, one of the main reasons why we do that is because, like any good scientist, when we go to Mars, we have a set of theories, we have a set of hypotheses. Based on those hypotheses, we design experiments, essentially, and choose the instruments that we'll bring with us. We're limited in terms of the amount of instruments we can bring. There's only so much we can launch. So we bring what we think we'll need, and then as with every mission, I'm sure once we get to Mars, we'll get there and realize, well, we got half of it wrong, or well, this looks a little bit different, or well, I got this answer, but not this one, and I would really like to have X, Y, and Z other instrumentation to figure it out, right? But once you're on Mars, it's gone. You can't just add instruments anymore. So being able to cache interesting samples, which we identify as interesting with our instruments, and then bring them back, is a huge benefit for the scientific community, because that means that, we'll have these instruments here. We can then use whatever instruments we'll have those samples here. We can use whatever instruments we have at our disposition to analyze them, and we can even make new instruments to analyze those samples. So I can't even imagine the amount of PhD theses that are going to come out of it. But it's estimated that something like a 20 sample cache could bring about a century's worth of science to be learned about Mars. And then in addition to all of that, if science wasn't good enough for you, Perseverance is also preparing for humans. So let's talk a little bit about how it's preparing for humans, and then we'll talk about the other instruments as well. So this is sort of an exploded view of the rover, and there are a few instruments on the rover that, in addition to doing science, are specifically helping for preparation for humans. So one of them is on here. We have a weather station and some wind sensors. We usually bring a weather station on every one of our missions on Mars that allows us to understand the atmosphere, the seasons, the regional variations, which is obviously very important when you're preparing for humans. We also have a ground penetrating radar here called RIMFAX, which can essentially see below the surface of Mars. It will analyze the structure below the surface of Mars. And that's important if we ever want to build. If we find that there's lava tubes or things like that that might be livable below the surface, anything like that, that's what the ground penetrating radar will tell us. But one instrument that I really like, it's probably my favorite. It's called MOXIE, and MOXIE is here in the body of the rover, and it's a technology demonstration, actually. And what it's going to do is it's going to perform what we call in situ resource utilization. So what it's doing is it's going to take some of the Martian atmosphere and extract the oxygen from it, and essentially showing that you can create oxygen on Mars. Now, the Martian atmosphere is about 1% of the Earth's atmosphere. It's not breathable in any way, but it does have compounds that have oxygen molecules, and that's what MOXIE is doing, is going to extract them. It's a tech demo. It's very small. It's probably going to produce, it has the ability to produce about 1/6 of what a normal human would need in a given day in terms of oxygen. But the whole point is that we've never done this on another planet before. We've never created resources from local resources. So if we can demonstrate that we can create oxygen on Mars using existing resources, that's a huge demonstration, because then we could bring a bigger version of MOXIE with us when we send humans to create oxygen for them. So that's kind of how we're preparing for humans there. But there's also a number of other instruments, of course, on board. We have some spectrometers and imagers on the arm. We have an imager on the mast itself. Actually, I think the full rover has something like 27 cameras, including being able to take video and zoom. What I really like about SuperCam is it also has a laser, which allows you to ablate the surface of rocks. And the reason why that's interesting, right? If you've ever played with rocks at all or broken a rock apart, you'll always notice that the inside of the rock is not quite the same color or content as the outside. That's because the outside is weathered. So we use the laser to remove that weathered surface of the rock and really be able to see its composition. And that's what that laser, in addition to being cool, that's what that laser is for. There are cameras pretty much all over the rover, obviously on the mast here, but on the front and back, There's an upward pointing camera on the deck that allows us to look at the weather. And then very neat and new also for this mission is that we are also carrying a microphone with us. And so that will allow us for the first time to hear the sounds of Mars. And that means that we'll hear the wheels driving when it's moving around, the laser zapping and things like that. So I'm quite excited actually to see some of that data come down for the first time. Okay, so here's a little bit of an overview of the mission timeline. So, you know, these missions don't just come about overnight. I think the idea for Perseverance came around back in 2012, 2013, basically shortly after Curiosity landed. And we're actually sort of a big sister of Curiosity. We've reused much of that design, right? So we were not starting from scratch. The landing site was selected around November 2018, but that was kind of a long process that involved science team members from all over the world where they presented different possible sites and then eventually narrowed it down to the one site that they wanted to use. And that site is Jezero Crater. And Jezero Crater, you know, is a really cool target for astrobiology because the crater is actually an old lake bed. Obviously, no more liquid water on Mars anymore, but there used to be liquid water. So it's an old dried up lake bed that most importantly has a river, well, an old river that used to flow into it. And then another exit point, the river also flowed out of the lake. And that's important because it means that there was nutrients and that were being flowed through that river, through that lake. It wasn't just a static lake. And specifically where we're hoping to land is at the delta of where that river meets the lake bed. And that's what you're seeing here. By the way, that's false color. That's just showing you mineralogy. Mars is not that pretty. But what's important there is river deltas. You know, we think that there's a lot of really interesting sediments that will be there on Earth. Deltas, if you look at river deltas, that's often where it's a very fertile area. There's a lot of history. That's usually where, you know, towns and civilizations have built because of that fertility. And so again, we're looking for analogs, right, of what we know about life on Earth and are hoping that Jezero Crater in particular will be interesting to look at. And one of the reasons why we're able to land at Jezero Crater, because we haven't been able to go there before, and here's a map sort of where other missions have landed, and Perseverance is landing over here, is because we have a new technology called terrain relative navigation, which allows us to fine-tune our landing site as we're landing. So it's an automated system, which as we're landing is going to look at the area and choose a safe area for the rover to land on. And that allows us to land in some much more interesting areas than we've done in the past. Because usually we were constrained to safe areas to land to, whereas as you can see from this image, we are definitely not landing, you know, not everywhere in this image is safe to land on. Certainly some of the areas over here are very flat. But the whole point is that as the rover is landing, it's able to pick out the safe areas and choose to land there. A little bit like Neil Armstrong and Buzz Aldrin did, you know, as astronauts picking, if you've ever seen the landing sequence of Apollo 11, they're sort of looking out the window at the craters and everything and sort of looking like, oh, it looks flat over here, right? And I have this much fuel, I think I can make it. That's pretty much what the rover is doing as it's landing. So here's the meat of it. How do we design and build a rover? And so that design and build started somewhere around 2014. I joined the team more recently, actually, in 2019. So I've been on the team for a couple of years now. And specifically, I was part of the team when we were doing the systems test and assembly. So I'm going to show you this video here, which gives you a little bit of context of what it looks like to build a rover. And it goes a little bit quick, but I'll try to talk over some of the aspects of it. So you're going to see things like the cruise stage and the descent stage. So this is the cruise stage. That's where the solar panels are going to go. This is the descent stage and the jetpack that's tied onto the rover as we're landing. What you're seeing here is the full cruise stage. That's the housing essentially that the rover is in during its sequence. One of the things that, you know, we build this rover on site. This is our campus that you're seeing. One of the things that people don't realize is these things are really big, and moving them around is quite a process. So what you're seeing here is a different set of tests. You saw how we build the wheels. We do a set of functional tests. We test pretty much everything. You know, where we test, you'll see the arm moving. We took it up to another area to subject it to the light conditions and the the temperatures that you're going to see on the way to Mars. And it takes quite the team. Here we're doing functional testing, looking at how we're going to core. You can see everyone's wearing bunny suits. This was filmed before COVID, so we do actually wear suits and masks all the time when we're building this. This is a clean room, and actually the room that this is built in is the same room where every mission, in fact, I have a picture. Let's see, the next slide, I think. There it is. This is the room that the rover is built in, and it's the same room that every mission that's built at JPL is built. Now, not every mission that JPL works on is built at JPL. For example, I worked on the InSight mission, and that was a collaboration with Lockheed Martin, so that was built at Lockheed. But we certainly do build a lot of our own missions, and they are built here in this clean room. And the reason why, everyone in the pictures or in the video were wearing bunny suits and masks is because of contamination. We actually don't want to contaminate the rover. If we're looking for life on another planet, we certainly don't want to be bringing our own life there, because then if we find evidence of life on Mars, we won't know if we brought it with us or if it was there in the first place. So we have to keep the rover incredibly clean, and there's a whole domain of planetary protection that deals with making sure that the rover is clean. So a little bit of a quick tour in lieu of you being able to see it in real life. Back here is the Wall of Fame, where there's badges of every mission that's been built at JPL. And hopefully, eventually we'll get the Perseverance Rover badge on there as well. What you can see here is Perseverance. Here's the cruise stage that has the fuel and the solar panels that are currently powering the rover. Looking for and then here's the descent stage, that jetpack I was talking about, which is supposed to lower the rover to the surface of Mars. One of the cool things is that this is on map. I can walk to it whenever I want. In fact, there's a gallery. And so it's pretty fun, and I feel pretty privileged to be able to just see and participate in a rover being built on another planet. And I really like to share this picture, actually, because these are some of my friends, right? The day that they installed the mast on the rover. And it's just so cool to be able to say that, my friends and I are building a rover that's going to Mars, right? Like, that is my job. And it's pretty incredible. I have to admit, it's long hours. It's a lot of work, but it is also incredibly satisfying to say that, I get to build something that's on its way to Mars and build it with my own hands and with my teams, my friends and my team, right? So that is quite an incredible part of this job, for sure. So here, let me share with you, hopefully this works, another test that we did. So what we do is we do a set of environmental testing when we go to Mars. And basically we put the rover through all of the environments that it's going to see on its way to Mars and on the surface of Mars. And we did that through a period of 4 months back in 2019, a very intense 4 months. So here we're doing a spin test that allows us to get the mass property for the vehicle. That's important for both the rocket and also just to understand where the center of mass is of the rover, for example. Here's where we assemble everything. You'll see it going to the cruise stage, and then it'll get shaken around. There it is. So we assemble, we put it on the shake table, and we literally shake the rover to subject it to some of the environments that it saw during launch, but most importantly, the environment that it's going to see during landing. Also, during the landing sequence, as it's landing, the mobility system gets deployed. So that's what you're seeing here happen. So that was tested too, making sure that everything behaves as expected. Quite the process, as you can see, to assemble and disassemble everything. This moment here is the first time that the rover stood on its own feet. It was quite the moment. That was the first time that we put it down on the ground. And here we're putting in a special environmental chamber. And we did two things in that chamber. First is that we set up what we call Mars Light and did a solar test that gave us thermal information about what the surface of the rover would look like, as well as visual information with under Mars Light. Then we sealed up that chamber, pulled out a vacuum, backfilled it with a little bit of atmosphere, and also did a thermal vacuum test where, I'll just pause it 1 second and continue talking about that, where we essentially mimicked the Martian environment and did functional testing to make sure that the rover could behave properly in that environment. And then finally, some of the most important tests that we've done here is the sample caching test. The sample caching system is the most complex addition that we've made to this rover. It has its own internal arm, which means that we have a robotic arm that takes a core, takes it out, passes it to another robotic arm that passes the sample around. The sample gets imaged, analyzed, and sealed. So quite the process. And then finally, I'll talk about that one some more because the test I got to participate in just over a year ago, and I can't believe it's only been a year, is the drive test. And this was the first and only time that we drove this rover by itself in ATLO, so in assembly test and launch facilities. And it was quite the test. So I'll actually show you, hopefully in my next slide, a video of that drive. Here it is. So this test happened, as I mentioned, just about a year ago. It was December 17th of last year. And I was actually in a room behind there operating the rover. But this whole test was the first time that we'd driven the rover, and actually the only time. So we set up a ramp for it. We made it do some turns. It went over and around the ramp and came back around. And that allowed us to make sure that we had all our instrumentation the correct way, that we knew how to operate this whole system as a whole. And it was quite the test, right? It seems, whenever you say like, oh yeah, we drove it for the first time, we're going to drive every day on Mars. But the first time you do it, it's also part of us understanding how does this beast work, right? How do we make sure that everything is set up correctly so that the rover can drive? So it was definitely a fun test. It was meant to be a 4-hour test and lasted 12 hours, as everything does in engineering. Nothing ever goes the way you want it to. But definitely a memorable day for my team and I. Okay, so then launch, right? So we finished building the rover and testing it back in about February of 2020. It then shipped out to the Cape Canaveral. It flew out of Florida. And right around then is also when COVID hit. So actually a lot of us were meant to go out there to help out with some of the testing, and I was, meant to go out there for the launch. We didn't get to do any of that. We all stayed home and supported the testing remotely and the launch remotely. It was kind of a shame to not be able to see it with our own eyes, but obviously that was the best thing to do for our safety and the safety of others. And it was still a moment that we enjoyed. I like showing this picture. So as I mentioned, we shipped around February, and we actually fly the rover out there and then bus out all of the equipment that goes with it. Finished some testing and assembly, put it in its cruise stage, and then I kind of call this sort of the Amazon Prime of rockets, or rocket fairings, because this is, you saw for scale earlier, this is the cruise stage, right, that you saw in all those videos, and this is the fairing, much bigger than what we need. And the reason why it's so big is because we don't custom build rockets, right? We buy a rocket off the shelf. In this case, and it's an Atlas 541. So we buy a rocket from United Launch Alliance in this case, and they just have different sizes. And typically they have fairings this big because when you have a rocket this big, typically for them, it's because you're going to Earth orbit and just sending something really big. In our case, we needed the fuel, but not the space. And so that's how we ended up with such a small thing in a big package. But I always kind of find it a little bit funny to show that picture. So launch day went off without a hitch. We launched on July 30th. I think it was something like 4 in the morning LA time, very early. But we launched right at the opening of our launch window. There was a storm coming later that week, so we got very lucky that everything went properly and we launched on time. And we are currently on our way to Mars. And I actually just checked. We've traveled so far about 202 million kilometers, and we've got about 90 million kilometers to go. So we're about 2/3 of the way there, and we are landing in 73 days. So we'll be landing on February 18 of 2021. So we have 73 days to go. And we've certainly been busy during that time, and I'll talk to you about what we've been doing. So far I've talked about all of the testing that we've done of the rover, right? We put it through all of the hoops and it worked through environmental testing, functional testing. We tested the hardware to make sure that it would survive all of, and that it would behave as expected. But the other key piece of complex systems like that is humans. There's a team of people that drive that rover, that operate that rover once it gets to Mars. And so we also test the humans in the system, and that's called operations readiness testing. And so we have operations rooms, and right now we're doing sort of a hybrid of remote and in-person operations. And we put ourselves through tests. So we use our test beds, and you've seen a few of them, and I'll show you a few of them. And we use essentially Earth replicas of the rover and of the brains of the rover to mimic a day in a life, a week in the life of the rover. So for example, next week, I will be participating in operations readiness test, which will mimic the first 5 days on Mars to make sure that we know exactly what we're doing those first 5 days once we get on Mars. And actually for that particular test, the test leads, the test operators, are actually going to inject faults into the system. So we call them gremlins, and they're going to inject errors or problems, possible problems, again, to test us to see how we react to it and whether we know how to fix problems when they happen. So it's definitely quite a process, and we actually have to be certified. So I actually have to pass a test to be able to operate the rover in the position that I'll be in for both landing and surface operations. So definitely quite a process. That was me thinking I was done with tests after a PhD. Not quite. Anytime you do Mars, anytime you do operations, you have to be certified for those skills. I mentioned that we have a set of test beds. So a couple of the ones that I get to work with. This is Scarecrow. So Scarecrow is a mobility system test bed. And by that, I mean that, you can see it has the wheels of 2020, but not much else, right? It doesn't have much of a brain. It doesn't have a mast or anything, just a set of cameras. That's why we call it Scarecrow. But what's important with it is that Scarecrow is a third of the mass of Perseverance. And why is that important? Well, Mars has a third of the gravity of Earth. So, if you remember, force is equal to mass times acceleration. Acceleration is gravity. So if you want the same forces on your suspension system as you will on Mars, here on Earth, well, you can't change gravity. We're kind of stuck with what we have. So we can change the mass. So if we use a third of the actual mass, that gives us the same weight, the same force, and therefore that allows us to test different parts of our mobility system related to how we handle different terrains. The other cool testbed that we have that I work with very closely is called Optimism, and Optimism is a replica of Perseverance. It's an exact replica. Right now, it doesn't have the robotic arm in this image because the robotic arm is in another test venue. We often sort of separate components so that some end up in some venues and others because there's so many of us that want to test. And in this case, the mobility team was mostly focused on driving, so it needed the mass and the wheels, but not the arm yet. So that's how we kind of double up on our time. But other than that, it's a replica. The only other difference is it doesn't have the radioisotope source. It has a giant cable plugged into the wall, and that's how we that's how we give it power and talk to it. So that is pretty much the only difference in terms of size and components. It's functionally the same, and we drive it around. What you saw in these two pictures is the Mars yard, which is basically a big sandbox that is set up like Mars, and we have rocks and slopes and things like that. And I get to drive around a rover in a sandbox. That is literally my job half the time. So I'm going out there actually tomorrow morning at 6 in.the.morning to drive out the rover and do some testing. So definitely kind of a fun part of the job. It's kind of fun to go out there in my hiking boots and crawl under the rover and repair things, for example, when I need to, which I did earlier this week actually. So I want to make sure we have plenty of time for questions. So I'm going to wrap up here with a few things. So one of the things that I wanted to highlight for me is that this mission is special for me for a reason, and that is that my first time interning at JPL, I actually interned at JPL twice before I became a full-time engineer there. And my first summer interning at JPL, you see that picture here on the left, was back in 2012. It was the summer of 2012. And that was the summer that Curiosity landed on Mars. And so I was I was an intern there, and I got to see the team land this rover. I wasn't part of that team. I was working on something completely different, but when you have a lab and something this major is happening, everyone was watching a landing, everyone was together for landing. So it was definitely very cool to see the rover, to see the team landing that rover on Mars, seeing the images come back, seeing the team come together and achieving incredible things on Mars. And I remember being an intern and thinking, I think that's when I really fell in love with JPL and thinking, wow, I really want to be part of the team that does this the next time, right? And because it's history changing. It's incredible. You're writing history books and science books as you go along when you do these missions. So, and then here's me on the right, that same picture you've seen a couple of times now. And so, all that to say, sometimes it's long hours, sometimes it's difficult, but it's definitely so rewarding to be part of the next team that's going to, land that next big rover on Mars. And it's really come full circle for me to be able to do that. And just to give you a perspective, it really takes a village to do this. This is not individual contributions that get there. And actually, one of the incredible things to think about when you're working on such big, complex systems is that there isn't actually a single person on our team that fully understands every single part of this rover. There just isn't. It's just too complex for a human to fully understand every single bit. So, we rely on each other, and it's taken a team of well over 1,000 people coming together, each understanding our pieces and understanding our interfaces and collaborating with each other to make these things happen. And that's one of the incredible things when you work on these types of projects, is that you're literally working on something that's bigger than yourself. You're working on something that can only come together by a group of people, right? And that's kind of, that's such a beautiful thing to be able to say and to be able to be a part of. And often, for those of you out there who are maybe students or are thinking about working in aerospace or anything like that, or wanting to become engineers, I often get the question, well, what's the one skill, right? Like, what's the most important skill to become an engineer? And I will tell you, sure, maths and physics is important, and you should stick with school, obviously, because you do need those degrees. But at the end of the day, I can teach you math and physics. I can't teach you how to be a good team player. I can't teach you how to work in a team, how to collaborate with others, how to listen to others. That's a skill that you have to develop for yourself, right? I can teach you an equation. I can't teach you how to behave. And so to me, teamwork and leadership and being a good team worker and listener is way, way more important than any of those other skills. So, if you're in school and I remember even through college having these group projects and being like, oh, why do I have to work in a group? It's so annoying. Now I have to gather other people. We have to work a schedule together. There's always one that doesn't show up or whatever. But honestly, some of those group projects taught me the best of lessons, right? And actually some of the people I worked on these groups I work with now. So, all that to say, don't dismiss those. There's a reason why you have group projects at school, and it's because of things like this, because in real life, to do these things, you have to do it in a team. So with that, just this last screen has a bunch of resources for you. There are Instagram, Twitter, Facebook accounts where you can follow the Perseverance Rover. That pretty much our social media team is posting videos and information pretty much daily right now in the last 100 days until landing. As I mentioned, we'll be landing February 18 of 2021, which is coming up. We'll be landing, I think it's about noon Pacific time, so about 3 p.m. on the East Coast. And it will be live broadcast on the NASA YouTube channel and on all of the social media channels as well. So, put it in your calendar. Please join us and watch that happen. We're hoping to get the sort of first images from Mars pretty much as they come down. And I will be on console that day, so I will be in one of those rooms, socially distanced from other people, but I will be there, and because I'm part of the team on the first day once we land on Mars that makes sure that the rover is safe and that we know where we are and things like that. So with that, I am going to hand it off to questions. I think that there's probably questions in the chat, and we'll see how many we can get through.
Yeah, so thank you so much. That was incredible and so inspiring. I'm going to help you moderate the Q&A, so you won't have to do that all by yourself. Don't worry. So let's see. We have quite a few to cover. So let's start at the beginning. Nolan would like to know, on the Perseverance rover, have you used a larger parachute than the Curiosity rover?
No, I believe that it's a very similar parachute. I do think that the material is a little bit different because we had to redo the testing and take that with a grain of salt because I'm not part of the team that actually built the parachute. But I do know that we were actually constrained in size and mass because we wanted to reuse as much of the system as possible, right? So we have pretty much the same landing system, the same parachute design, things like that. The Perseverance Rover is in the same cruise stage. That shell that you saw is the same as with Curiosity. It's just Perseverance is a little bit heavier and we pushed the envelope a little bit more, used up a little bit more of that fuel margin, but other than that, it's very similar.
Awesome. Thanks so much for that. The next question is from Chuck. I think our biggest question would be, what tests will you perform to determine if bacterial life exists on Mars?
Oh, that's a good question. So I am not a scientist, and so probably not the best person to ask, but I do know that we have a set of instruments that allows us to at least start getting an understanding of whether there might be complex molecules in those sediments, right? So we have a spectrometer, we have some microscopic imagers, for example, that allow us to look at those components. And actually the science team back a few years ago went out to Australia, of all places, but there are places that look a little bit like Jezero Crater that have those sediments and those sets of rocks that are usually full of life on Earth. And so they went out there and tested their instruments on those rocks to understand what signatures they're looking for. So they're looking for certain types of signatures from those instruments that would indicate, that would give us indicators that there might be life. But really it'll come down to, if we think that those are interesting targets, we will then capture, put them in tubes, seal them, and then bring them back and do another set of chemistry and experiments on them here on Earth to understand really what we're seeing.
Yeah, definitely. Analog stuff is definitely my jam as a scientist / future planetary explorer, hopefully. So love that. Okay, the next question is from Felix. Is Perseverance ever coming back? Will she perform tasks autonomously?
So Perseverance is never coming back. We don't bring back our rovers. They are much more useful on Mars than they are on Earth for us. So we will drive her for as long as she'll let us. And as I mentioned, Curiosity's been there for 8 years and she's still trucking. So we expect that she'll, Perseverance, even though her, primary mission is 2 years, and that's the time that we want to, it's one Martian year, the time that we want to take those samples. We're not bringing the full rover back. We are bringing back the samples, hopefully. So if we get a cache of samples that is interesting and deemed worth bringing back, then we will bring them back through another mission that will go pick up those samples and launch them. But we're really only bringing the samples back. It's very expensive to launch anything from any planet, let alone launch fuel here to land on Mars to launch something back. So we're limited in terms of what we're able to bring back. In terms of autonomy, yes, there is some autonomy on the rover. I talked about terrain relative navigation when we're landing, but one of the pieces of autonomy that I'm most familiar with, well, there's two actually. So there is, the rover is actually able to self-drive, which is pretty neat. Now, self-driving on Mars is a lot different from self-driving on Earth. The advantage is there's not other cars or humans or dogs to avoid, but there's also no roads and no Google Maps. So what the rover does when it's self-driving is that as it's driving, it actually images the terrain in front of it, analyzes the obstacles, decides based on those obstacles and the target of where it would like to go, what path it should take. And then it takes that path and then takes a next set of images and so on. So it looks 5 meters in front of it at all times. And using that, it can drive about 80 to 100 meters an hour. It's fairly slow. And so we think that, we'll be using that autonomous mode quite regularly once we're on Mars because we want to travel large distances and get a varied set of samples. So we expect to be able to drive, about 200 meters a day autonomously. Now that seems like not very much, but the record of distance traveled on Mars is, I can't remember if it's held by Opportunity, and I think it drove 230 meters. That was like record breaking. So what we're talking about here is breaking distance records every single day once we're on Mars. So it's quite the technological advancement from previous missions.
Yeah, that's incredible. Okay, this question is from Joshua, and why does the rover need a second arm for sample caching?
So mostly it's just a design that we've done. So the big robotic arm is the one that picks up the sample and drills it, right? So that's a big arm with a lot of momentum associated with it. It then captures that sample and puts it in the belly of the rover. And then from there, you want to be able to, you don't want to be just put the sample in one place and not have it move anymore. You want to put it in a tube where it can be analyzed and then sealed. So it needs to be passed around between stations. So there's a much smaller robotic arm that allows it to pass it around between stations and finally seal it and put it in its spot in the rover. So that's just a design decision that was made to enable that process.
Interesting. I would have never thought about something like that, but that's really cool. This next question is from Elspeth, and it is, where Perseverance was being tested, there's a big American flag. So I'm wondering, is the Perseverance rover 100% American owned?
So it was tested here at JPL. As I mentioned, JPL's in LA, so California, which is the United States. So it is a NASA mission. However, not every component on Perseverance was developed by NASA. There were instruments that were provided through collaborations. So we have a couple of European instruments on there. There are also instruments that were built at other institutions outside of JPL. For example, MOXIE was built at MIT and the Haystack Observatory, things like that. So each instrument was built in a different place, but yes, in the end, it was all assembled and built here, and it is a NASA mission.
Yeah, it definitely takes a village, as you said. This question is from Anita and John. Is positive life determination possible in situ by the onboard instrumentation, or will analysis of the Earth return samples be required?
So I'm a little bit out of my depth here because I'm not a scientist, but I do believe it basically depends. It depends on what we find. It depends on how clear the signatures are. So possible with the instruments, yes, but it really depends on what instruments, on what they find. But certainly at a minimum, the identification of interesting samples to bring back is absolutely something that they're prepared to do. But if you're interested more in the science part of it, I would encourage you to look at some of the resources I posted. There are links out there to science papers and talks that our principal investigator Ken Farley is an excellent orator and has done a bunch of presentations on this. So I would trust him a lot more than me on those things.
Awesome. This one is also from Anita and John. What are the differences besides instrumentation in the system from Curiosity?
Wait, hold on. Could you repeat that question for me, please?
Yep. What are the differences besides instrumentation in this system from Curiosity?
Oh, okay. So it's a little bit heavier. As I mentioned, the arm is bigger. There's a lot more cameras, the microphones. The drive system is completely different. So the wheels are different. They have a different pattern. They're made of a different material. We actually have a second computer on board that allows us to have some of the autonomy. So the terrain relative navigation, for example, that's all through this additional computer. So a lot of upgrades. So a lot of things are similar, but also quite a few upgrades on that rover.
For sure. This one is from Ilyas. In the drive test, is any lag artificially added?
No. So the rover really does drive that slowly. Yeah, so not in the drive test, although we do add lag in the operations readiness test. So one of the things I didn't talk about is how we operate a rover on Mars. And actually we don't just joystick it, right? Like it's not just like I tell it to go forward, it goes forward and sends me information. And the reason for that is because the way that we communicate with rovers on Mars is via radio. And radio travels at the speed of light, which is, as fast as we can go, but still not all that fast when you're talking about something that's millions and millions of kilometers away. So in a given time of year, it can take anywhere between 7 to 12 minutes for a piece of signal to go from Earth to Mars, and then another 7 to 12 minutes to come back. So if we were to drive around, via joystick, that lag would be horrible. It would take anywhere between 15 to 30 minutes to get a response to every action. So we don't operate like that. What we do is that we actually work during the Martian night. So in the afternoon, early evening, the rover will send us a bunch of information, tell us what it's done all day, send us telemetry and images. We will look at it, analyze it, make sure the rover's okay, that it's done what it's supposed to do, understand what we're seeing, and then we'll make a decision as to what we want to do the next day. We'll build a plan. We'll code up that plan as a team. We will bundle that plan, send it up to the rover so that it gets to it before the morning on Mars, so around 7, 8 a.m. on Mars. The rover will wake up, look at its plan, and execute it for the day, and the cycle repeats. So that all sounds good in terms of, okay, we just work on the Martian night, whatever it is over there, and but one of the subtleties there is that, so Perseverance has its own time zone on Mars that it's going to be landing in, obviously, so daytime and nighttime start at a certain time, but a Martian day is actually about 24 hours and 40 minutes, more or less, which means that it's a little bit longer than an Earth day. And that means that even though, we might start at 6 p.m. Mars time every day for our operations, that actually changes by 40 minutes every day here on Earth. So, if I might start at 8 a.m. on Monday, it'll be 8:40 on Tuesday, 9:20 on Wednesday, and so on. And soon enough, you're working through the night here, and it shifts a little bit every day. And I always tell people that it makes for scheduling happy hour pretty much impossible, because you never know what time you'll be on when you're on Mars time. So we do that for the first 3 months actually after landing. And then after that, we kind of alternate and work every other day so that we're not always working on strange Mars time.
Right, yeah. And I think another question related to that here would be, since it's an international team, I assume that there's a lot of time zone differences even here on Earth that have to be put up with in addition to the ones on Mars.
Yeah, so actually everyone has to work on Mars time. It doesn't really matter where you are on Earth. That kind of makes it easy. It's an even playing ground, right? It's like, well, we're working on Perseverance time. So yes, we do have collaborators in Europe, for example, or even on the East Coast, and they all work at the same time as us. And sometimes that's pleasant for them and not great for us. And sometimes that's the opposite way around, right? And so it makes it fair, I guess.
All right, Max asks, what Martian factors had affected previous missions, and how will this rover manage those known factors?
Well, okay, so there's a few examples. Obviously, there's a whole lot out there, but a couple of big ones is, you probably know the Spirit and Opportunity rovers. They died eventually because of dust, right? And they died in a giant dust. Opportunity especially died in a giant dust storm a couple of years ago. And the reason why that affected them particularly is because they are solar powered. They're smaller missions, and so in our case, we don't have to deal with dust as much because we have a radioisotopic source that keeps us powered, and so that really helps us. But we're also bigger, so we couldn't do it just with solar power. But we have learned to deal with dust. For example, we have covers on our cameras that we can close on certain cameras to make sure that they don't get dirty, things like that. So that's one example. Another example of a big lesson learned, and the reason why one of the upgrades that we did on Perseverance was to update the wheels, for example, is that Curiosity actually suffered some pretty bad wheel damage on its wheels. And the reason why the wheels got damaged was because, well, we didn't quite predict what the Martian surface was going to look like, right? And particularly when there's sharp rocks on soft environments, which are not things that we often see on Earth, but does exist on Mars quite a bit, that caused damage to the wheels. So we saw that wheel damage, a few years ago on Curiosity, went back to the drawing board on Perseverance, did hundreds and hundreds of hours of testing on different environment with real wheels to figure out a system that we liked better. So that's an example, for example, of something that we've learned.
That's super cool. Michelle asks, Spirit and Opportunity had metal pieces from the World Trade Centers as part of the raw material for some of their components. Does Perseverance have something similar?
Yeah, actually, there's a few things on there. So the first is that we have chips that carry the names of millions of people on Earth. And so you were able to sign up to get your name written on that chip. And so if you did, it is on there, and we'll probably, it's on the deck. I know where it is, in fact. Another later addition was there's a plate for our first responders that's on the side of the rover. They are really the reason why we were able to make it on this launch opportunity. If you don't know, we can only launch to Mars every 26 months or so. The planets have to align a certain way. So if we didn't launch this year, if we missed our launch for some reason, because people got sick or because there's something happened, we couldn't have launched until 2022. And one of the big reasons why we were able to achieve that is because of our first responders, is because of the people on the front line who kept us safe. And so there's a plaque in their honor on the side of the rover.
That's awesome. Yeah, and thank you so much to any first responders watching this. You guys are heroes, so that would be a fantastic way to honor them. Antoine asks, is there a satellite orbiting Mars that will keep track of Perseverance? If not, how is the rover's position tracked? How accurate is this tracking?
So yeah, there is a number of satellites around Mars, actually, both US orbiters and European orbiters, and I believe there's an Indian orbiter on its way there, or already there. Can't remember from anyway. So there are a number of satellites in orbit, and so we actually use those satellites as relay stations for us. So the rover can talk directly to Earth using one of its radios and one of its frequency bands, but in order to relay like all the big images and all the big videos and stuff like that, we prefer to send it to the orbiters up in orbit, so much shorter distance, and then the orbiters relay that back to Earth, and that makes it easier for us. So that is how we talk to the rover. When we're landing, one of the orbiters is actually going to track the rover as it's landing on the surface of Mars, and that helps us localize us on the surface of Mars. But we don't use orbiters the way you would GPS, right? Like we don't use it to track each other every day. We can do that using our onboard instrumentation. So, and the most important thing we use actually is that we use the sun, right? Just like original explorers might have used stars to locate themselves in a direction. We use the sun. If we know what time of day it is and where the sun is, we can orient ourselves and we know our direction. And then based on our wheel odometry, the same way as you would in your car, we know how far we've driven. So we can keep track of the directions that we've given from imagery, from our instrumentation, and from outside objects, essentially, to figure out where we've been. And we have knowledge from our landing site of all of our travels. And that's actually part of my job, is to make sure that the biggest part of my job is I'm the one in charge of make sure we don't lose a rover.
Nice. That's a very large responsibility. Joshua asks, as a Canadian, am I legally able to work in the US space industry at like SpaceX or NASA, for example?
So you have to be, it's complicated, but there are different reasons, there are different laws, right, when it comes to working in the United States. So there's labor laws, you have to have certain types of visas, obviously, but typically at all of those companies, you have to be a permanent resident or a citizen. So you have to be a green card holder. And because there are commerce and international trade and arms regulation laws that dictate who is able to work on different types of components. So we certainly collaborate with non-Americans. As I mentioned, some of these instruments are European, right? I'm on the InSight mission. I worked very closely with the French space agency CNES, for example, and I was working on that instrument with them. And so I got to go out there. Actually kind of cool to get to use my French. They did laugh at me a lot for my French Canadian accent. But I never thought I'd use French at NASA. I certainly did. So there are definitely international collaborators, but the roles that you're allowed to take based on your citizenship just kind of depends. We certainly have people on our science team, for example, who are not American citizens.
Yeah, knowing multiple languages is definitely an asset, even if your accent may be embarrassing sometimes. Virginia asks, I think you mentioned this actually earlier, but you can reiterate, of course. What challenges did you face on your journey to where you are now, and how did you overcome them?
Oh God, so many. The amount of time a door closed and someone told me no, or told me I didn't belong or couldn't be there. It happened so many times. It started, when I was in high school, and even when I was a kid growing up in Joliet, we were the only non-white family there, and I was bullied in school because people didn't understand what a brown person was. And then going to high school, I had a career advisor who, when I told her I wanted to be an engineer, told me it was a male-dominated world and I should maybe reconsider that maybe I wouldn't belong there. Well, I don't know where she is now, but I definitely did not listen to her. But and then going through college, I remember I went to the University of Cambridge. I came from a high school where I was, one of the best at the school, right? Everything came easy. And then I showed up at the University of Cambridge and everyone there was one of the best at their own school. And I was way behind because some of these kids had gone to like the Eatons of this world, these really prestigious private high schools. My parents didn't have that kind of money. I went to public school. And so I was behind compared to them because I didn't have someone who tutored me that whole time and taught me all these things. But it certainly was a blow on, like, for any of you that are embarking into college or have just gone through it, you'll remember this, that it's hard the first time you threw up in college and everyone's as good as you are and you're struggling to keep up, and it's a lot harder than high school and there's no one there to hold your hand and you're far away from your family. So I certainly remember failing a whole bunch of exams my first year. In fact, I remember my tutor at school, at university, being like, yeah, you got to retake these. Like, we got to make sure you understand what you're doing here. Like, I don't think they had much faith in me when I first started. I ended up, winning awards for my thesis and my master's, but like I started bottom of the pack and had to work my way up, right? And so, the successes definitely came with hard work. And even when I came to the United States to do my PhD, the number of times I was turned down for internships for a reason or another, and eventually I got there. And the biggest pieces of advice that I have, or whenever people tell me, well, how'd you get through it? I think I'm like very stubborn. That probably helps a lot.
Yeah.
But what it comes down to is that doors are going to be closed. You're going to be told no so many times along the way. I've stopped counting, right? The amount of times, even now, the amount of times I get turned down for positions that I want, right? But it only takes one yes. It only takes one success. It doesn't matter how many times you fail. As long as you succeed once, you'll get there, right? And you'll get to, and it's worth it because you get to do something super cool that you love doing, right? Whether it be space or whatever it is that you're interested in. So I always say, don't let people tell you no. Don't let things. Disappointments are real, but pick yourself up, try again, right? And the other big thing is find allies, find people along the way who will help you, mentors. There's definitely been people in my life who have opened doors for me, whether I knew it or not. And those people, I thank them once you get where you are, but also lean on them. You're never going to do any of this alone. I didn't get where I am by myself, right? It's all, there's always people who are going to help you along the way, and there's no pride, right? Just take the help, reach out, take the help, lean on those people. And for those of you who are in high school maybe right now listening, I can tell you one story. I had a math teacher in high school who, I hated him for a while because he would make me work so hard. He would just like give me extra problems to work. He would always be hard on me, even though I was getting better grades than everyone else and getting through all the problems real fast. He was always really, really hard on me. And I always thought that was so unfair. But eventually, right, looking back, I discovered that he was doing all of these things to help me. So certainly, there are teachers like that in your life who like, he went above and beyond anything that he needed to do to help me succeed, right? And so, I know it's hard sometimes to be working from home in this environment. It's temporary, but those teachers out there that are helping you out, they, listen to them. Don't get too angry at them, please, because they certainly are the people that will enable you to achieve whatever your dreams are.
Yeah, and I think we can all speak for ourselves when we say that Kareem has definitely been a great mentor for a lot of the young people attending tonight. I'm seeing this Q&A, and almost all of us that are young people that I know have attended his courses. So that's pretty awesome. Be nice to your mentors, guys. Let's see here. We have quite a few questions and not very much time left, so I'm going to try to take a couple more. Which part of the testing and designing of Perseverance would you say was the most challenging? And this is from Camille.
Even though I was not involved with it, and maybe because I was not involved with it, it's a little bit mystical to me, but the whole sample caching system is an incredible system. And it definitely is the one that, we talked about heritage and the fact that some of those things we took from other missions, we had no heritage for this. We have never done this before, right? And it's a very complex system. It's essentially as complex as the rover itself, having to handle all these things and keep them clean. So definitely, I would think that to me that was the most complex system to test, and it's still being tested right now, right? We have an Earth replica again, and the one that will give us the biggest scientific return also.
Awesome. Okay, here's another one from Antoine. How will you make sure these future missions will be able to find those samples, considering they can move and be covered with storms, citing a couple of previous issues with those missions?
So we talked a little bit earlier about knowing where we are. That's how we're going to do it. We won't, we will, these, first off, these tubes are white. They have certain recognition features, but we should know exactly where they are, right? Because we know where we are. So basically, because of our mobility system and our ability to locate ourselves on the planet of Mars, we can, once we leave those samples, we will know exactly where we've left them, both in the local scale and the global scale. That will allow us to find them again.
Awesome.
It's like dropping a pin, right, on a map. That's exactly what we'll be doing.
Yeah, true. I mean, you got to keep track of them somehow. From Nadeem, we have what sorts of tests will Perseverance perform to assist future Mars human habitation, I suppose?
Yeah, so we talked a little bit about this, but obviously there's MOXIE that's going to be creating oxygen. We'll be looking at weather patterns. We're particularly interested in seasonal weather patterns and daily changes, things like that. And then RIMFAX, which is that radar, that ground penetrating radar, will be using that as we're driving on the surface to understand what's below the surface. And that structure of Mars is very important for us to understand what can be used, what might be below the surface, what can be built on there. But then most importantly, every time we land, we get more information about how to land on Mars, right? It's not like we've landed on Mars that many times successfully. It's still very hard. It's still a good chance we won't make it. So, that part of it is important because we learn, get yet another sample of how to learn on Mars. We understand the geology. We understand how to locate ourselves. So on a more global scale, we're just understanding more about Mars, which is also very important in terms of eventually bringing humans to Mars.
For sure. This question is from Alex. What is the range of the helicopter drone that is going to be tested, and does it have a nickname?
Yeah, so there's a helicopter that's currently attached to the belly of the rover, and it's called Ingenuity. And so it's going to be dropped from the belly onto the surface. And then in terms of range, it sort of depends. So the rover itself will be 100 meters away from the helicopter when the helicopter does its flights. And the rover acts as a relay. So the rover gets all the signals and the information, transfers that back to Earth. We talk to the helicopter through the rover. The rover also does all the imagery. The helicopter itself will do a series of tests, a series of technology demonstration tests. So the first flight, is just going to go up and come back down. It's about 10 meters. And then I think it traverses and comes back. So I don't know the numbers exactly because the Ingenuity team is actually a full separate project. I interface with them a lot in one of my roles. But I believe that it can do flights of like 100 meters. It is about, don't quote me on the exact number, but that's about the range, in terms of scale that it can do in a given flight.
Let's see here. We have one question from Richard. How similar is your role with the Perseverance mission compared to the InSight mission?
Very different. InSight didn't move. And I'm part of the mobility team now, so completely different. So on InSight, I was more closely working with the instruments. I was very close to the instrument team, helping them test and prepare for operations. And then during operations, I was one of the tactical integration leads. So when you're on a day-to-day, when you're building the plan and sending it up to the rover or the lander, I was the person who was sort of managing all the teams and making sure the plan came together, or one of those people, because there's multiple people that can do the same job. That part of the job, I'm actually doing the same on 2020 for operations. So that's the only thing that stayed the same. But on 2020, you know, I've been more focused on working on the mobility system, doing a lot of testing for that and for what we call surface guidance and navigation. So the part where, you know, talking about where we are and how we're oriented. And then my other job also on 2020 is that I'm the interface between the rover and the helicopter. So anything that has to do with operating the rover to support the helicopter mission is a part of my role as well. So no helicopter, no wheels on inside. So definitely pretty different.
Awesome. Well, I think we're almost done with time. Kareem, correct me if I'm wrong, but it's already 6:15.
Shall we do one last question?
Yeah, sure. One last question. Let's see. This is kind of a lot of pressure. This might be a good one to end it on. So are future missions already being planned, and how are you involved?
Yes, so we're already starting to plan the sample return mission, right? Obviously, it's dependent on this mission being successful. So I guess that's how I'm involved. I'm making this mission work. But, so it is obviously dependent on Perseverance working. But you know, there's already a team out there that's planning and designing a potential sample return mission, because once it gets the green light, we want to be able to get those samples, you know, in a timely manner. We might still not get those samples until like 2030, but for us, that's very close for us when we're talking about 8 to 10 year scales to develop missions. So at Mars, that's what's happening. But obviously, all across the solar system, there are a number of missions that are going on. Two big ones for JPL specifically is the Psyche mission. That's a mission to a metal asteroid that's launching in a couple of years. And then there's also the Clipper mission, which is a mission that's going out to a moon of Jupiter called Europa. And Europa is cool, you know, also another astrobiology target because it has, you know, it has a global ocean, a core, and a ice shell around it. So very different from Earth in terms of an astrobiology target, but a possible astrobiology target because it has that water and because it gets energy from tidal flexing. So they're going to investigate there whether there might be life on Europa. So those are the two big missions to look out for after Perseverance.
NASA has definitely made it tough to be an astrobiology nerd because there's just too many good things happening and not enough time. Well, thank you so much for these super informative and inspiring answers to these questions. I think we've gotten through a lot of them, so hopefully I managed to cover enough. But I'll pass it on to Dave and Kareem to say thank you as well.
Thank you, Emily, for moderating. That was fantastic. And Dr. Alibay, I'm speechless. This is your prepared material was fantastic, but the amount of information you shared with us during this Q&A, and it was inspiring. To give you an idea, all through the Q&A, more and more questions were popping up. There's another 24 questions sitting there waiting for answers. And this is the neat thing, is because we've got a couple of months till Perseverance lands, there's a lot of time for people to really learn about this mission. And so on behalf of all of us, I want to thank you for sharing your time, sharing your experience, and especially for the youth in our audience, sharing your journey. We really appreciate seeing the not just what you persevered to get to, no pun intended, to get to the point where you're at now, but also seeing the spark when you talk about your work and the things that you do from day to day. I mean, talking about getting up tomorrow morning at 6 to go out and drive on the Mars habitat. A lot of us feel that way when we look at the night sky and when we get out in the middle of the night to stare up at the heavens and at the stars. And so seeing that from somebody who's on the engineering side of space exploration is just humbling. So thank you so much. Dave, I'll pass it over to you for any last comments.
Well, I'd just like to reiterate our thanks. We really appreciate your talk. It was absolutely amazing. We have people from all over the place. There's even somebody from Costa Rica on the call. So really appreciate what you shared with us today. And maybe we can get you back at some point, maybe in about a year's time. And you can give us a follow-up on how the driving's going on the Red Planet.
Yeah, certainly about a year from now, we should have a lot more interesting information about the mission and everything that's happened. So I'll be out of Mars time next May. So yeah, about a year from now may be a good time to catch up again.
Super. Well, thank you very much. Stay safe.